Hello, this is Mr. Davidson. This lesson is going to be on lesson 10. So this is the last lesson specifically looking at logarithmic functions. There's still two more lessons that we're going to do on rate of change that we skipped in the rational functions unit. I skipped a video for lesson number 9 because Miss Bradley had a video for that lesson as well, so I figured I might as well just post that rather than try to record my own. Save some time and get more videos for you sooner. So this is lesson number 10, combinations of transformations. This is the second lesson for the week of April 13th to 17th, and I just need to open up the lesson so I can see it. So we're talking about combinations of transformations. The last video I recorded, which was actually 2 lessons ago, was just kind of reintroducing transformations and what they necessarily look like for logarithmic functions. We're going to start off looking at this function here. So y equals 3 over 2 log base 10 of 10 minus 2x plus 2. So we can rewrite that a little in order to make some of the transformations a little bit easier. So we'll rewrite the argument. I'm not going to write log base 10 just to reinforce the fact that writing no base of an exponent means log base 10. So again, if you don't see a base to a logarithm, that means we have log base 10. So I've just rewritten 10 minus 2x to give us minus 2x plus 10 plus 2. And the very, very, very important part for these horizontal transformations, if we have a horizontal reflection, or a reflection over the y-axis, or a horizontal shift or compression, we must factor the number in front of the x. So if we don't just have a single x there, we need to factor out whatever is in front. So we're going to factor out a negative 2, and it's going to leave us with x minus 5. That is how we know what horizontal shift we're going to have. This plus 10 means nothing until we factor out that negative 2. So very, very important that we do that factoring. We have quite a bit going on here. We have 4 different transformations. We have a vertical stretch by 3 over 2. That number out in front, a number multiplied by the whole base function, the whole logarithm, that's going to be a vertical stretch. We have an addition of the whole function. So we have a vertical shift, vertical translation up 2 units. So these are both our vertical transformations. We have a negative, so we're going to have a horizontal reflection. So a reflection over the y-axis. We also have a 2 multiplied by our x term. So we're going to have a horizontal compression. So you can either write this horizontal compression by 1/2, or horizontal compression by a factor of 2. Either way is okay. By 1/2 or by a factor of 2. Just be careful that by a factor of 2 doesn't mean that we're multiplying all of our x values by 2. We're multiplying by 1/2. And then finally, x minus 5, we have a horizontal shift, a horizontal translation 5 units to the right. So we have quite a lot going on there. I think I said 4. We actually have 5 different transformations, including that reflection. So we're going to see, what does this do to our original coordinates? So our original function log base 10 of x. Again, these are the same coordinates we've been looking at the past couple lessons. We're going to have the point 10, 1, the point 1, 0, and the point 1 over 10, negative 1. And we want to see, what do these transformations do? What's happening to our newly transformed function? So vertically, things affecting the y, we have a stretch by 3 over 2. So every single y value gets multiplied by 3 over 2. And this isn't quite clear in the completed lesson, but if we're shifting, I guess they do it later. No, they don't. So if we're shifting up by 2, we're adding 2 to our new y values. For x, we have a horizontal reflection and a horizontal compression by 1/2. So our x values get multiplied by negative 1/2. Then if we're shifting 5 units to the right, we need to add 5. So you'll notice here we're multiplying by 3 over 2. We're multiplying by 3 over 2. We're adding 2. We're adding 2. Everything happens exactly the way it appears in the equation. Horizontal, things happen the opposite. Here we're multiplying by negative 2. Here we're more or less dividing by negative 2. We're multiplying by negative 1/2. Here we're subtracting by 5. Here we're adding by 5. So every horizontal transformation that appears in the equation, the opposite is happening to our coordinates. So if we plug in our x and y values, negative 1/2 times 10, we get negative 5, plus 5, we get 0. This is not how these coordinates appear in the completed lesson. The shifts and translations they do after, they only take into account the stretches and compressions and reflections. So I'm showing you how we can do this all at the same time. Our y value, we're going to multiply by 3 over 2. So 1 times 3 over 2 gives us 3 over 2. Plus 2 or plus 4 over 2, we get 7 over 2. That's our first point. Second, 1 times negative 1/2, we get negative 1/2. Plus 5 or plus 10 over 2. Negative 1/2 plus 10 over 2, we get 9 over 2. 3 over 2 times 0 is 0, plus 2 is 2. And finally, 1 over 10 times negative 1/2, we get 1 over 20. Sorry, negative 1 over 20. It's multiplied by a negative. 1 over 10 times negative 1/2, negative 1 over 20. Negative 1 over 20 plus 5, so plus 100 over 20. That's going to be a nice round number, negative 99 over 20. So just 1/100th less than 5. Sorry, 1/20th less than 5. Y value, negative 1 times 3 over 2, we get negative 3 over 2. Negative 3 over 2 plus 2, negative 3 over 2 plus 4 over 2, we get 1/2. So if we compare this to our values, these are the values they list in the lesson. They're doing this shift right by 5 and this shift up by 2 after they have these points. So every single x value is going to get 5 added to it. So plus 5, plus 5, plus 5, we get these three values. These still need to get shifted up by 2. So if you add 2 to these three values, you get 3.5 or 7 over 2. Right, 0, sorry, I was going the wrong way. 0 plus 2, we get 2. Negative 1.5 plus 2, we get 0.5 or a half. So that's why these numbers are different than these numbers. If we compare our graphs, so if we plot these 3 points on our original function, we get that logarithmic shape that we're getting more and more familiar with. And our other 3 points, if we plot those, 0, 7 over 2, right, okay, so they did plot them correctly. 0, 7 over 2, 9 over 2 to negative 99/20ths, so just less than 5.5. We get these 3 points here. So we have, we can definitely see we have a reflection. We're moving in the opposite direction now. We are stretched out a little bit. These 3 points, we only go up 1 unit. From here to here, we go up 3 units. Oh, I'm looking at the wrong 3 points. Here we go up 2 units. Here we go up 3 over 2 units. So let's write down our characteristics. So our key features of our new function. So normally we have a domain x, the element of R, and we need x to be greater than 0. We need a positive number in the argument. Now, in our transformed function for the domain, now we're moving to the left of this asymptote at x equals 5. So x has to be less than 5. Anything greater than 5 is going to give us a positive in this set of brackets times a negative 2. It's going to give us a negative argument of that log. And remember, that's what we cannot have. Our range for these logs is always y is an element of R. And our equation of our asymptote, which normally is at x equals 0, that gets shifted 5 units to the left, and now it's at x equals 5. So these still show our transformations. Here we're getting a reflection, so this greater than symbol turns into a less than symbol, and we're moving 5 units to the right, so we go from 0 to 5. Our range was all real numbers. No transformations are going to change that. We still cover all real numbers, and our asymptote changes as such. Let's grab a new sheet of paper here. Our y-intercept y-intercepts, they always occur when x equals 0. So if we look at our function, which was y equals 3 over 2 log base 10 of 10 minus 2x, this is the original function we were given. We want to know what happens when x equals 0. So we're going to plug in x equals 0. So 10 minus 2 times 0 gives us 10 minus 0, or just 10. Log base 10 of 10, 10 to the power of what gives us 10? 10 to the power of 1 gives us 10. So that whole logarithm is just going to equal 1. 3 over 2 times 1 is 3 over 2. Plus 2, and rewrite that as 4 over 2. And that's going to be 7 over 2. So all of that, we have a y-intercept at 0, 7 over 2, or 0, 3.5. Our x-intercept happens when y equals 0. It always happens along the x-axis. So y has to be 0. We're going to now sub that into our equation. So 0 equals 3 over 2 log base 10 of 10 minus 2x plus 2. Now we have to solve for x. So we're going to slowly pick this apart. We can start off by moving over 2. So negative 2 is 3 over 2 log base 10 of 10 minus 2x. If we have a 3 over 2 being multiplied by our logarithm with the x in it, then we can multiply both sides by the reciprocal. So negative 2 times 2 over 3. 3 over 2 times 2 over 3 is just 1, so that's going to cancel that out. And we just have log base 10 of 10 minus 2x. Minus 2 times 2 over 3 is negative 4 over 3. Log base 10 of 10 minus 2x. And so now we want to get the x out of the logarithm. We need to switch to exponential form. So our base is 10 to the power of negative 4 over 3, and the argument becomes isolated on its own side. So 10 to the negative 4 over 3 equals 10 minus 2x. We'll move that 10 over. 10 to the negative 4 over 3 minus 10 equals negative 2x. And if we divide both sides by negative 2, 10 to the negative 4 over 3 minus 10 over negative 2. So we're going to plug that into our calculator. So 10 to the power of negative 4 over 3 minus 10. We're dividing that by negative 2. We get 4.98 approximately. So our x-intercept is at approximately 4.980. So that's how we find our x and y intercepts. y-intercepts, we're plugging in x equals 0. Y-intercepts, we're plugging in y equals 0. And we're solving for whatever our other variable is. Look at one more example. We'll look at the function y equals -5 log base 10 of 2 over 3x plus 8 over 3 plus 5. So again, first thing we need to do, we don't just have an x, we don't just have one x, we have 2/3 x. So we need to factor out 2/3 in our argument. So we're going to factor out 2/3, we divide by 2/3, we divide by 2/3. 8. So we need to see 8 over 3 divided by 2/3. That's the same as 8 over 3 times 3 over 2. So our 3's cancel out. We get 8 over 2 or 4. And now we can deal with our transformations. So our original function, we have log base 10 again. So our original function is this log base 10 of x. So our original points, we're going to use those same 3 points we've been using. 10, 1, 1, 0, and 1 over 10, -1. And now when we transform this, horizontally, we have 2/3. So that means we're going to have a stretch by the reciprocal. We're going to have a stretch by 3 over 2. We know it's a stretch because 3 over 2 is greater than 1. So we take the reciprocal of 2/3 and we do the opposite of +4. So that means we're shifting left by 4. So we're subtracting all of our x values by 4. For the y, vertical transformations happen just as we see them. So we have a vertical stretch by 5 as well as a vertical reflection. So a reflection in the x-axis. So all of our y values are going to get multiplied by -5. And then we have a vertical shift up 5. So we're going to add 5 to all of our y values. So now 10, we plug that into our x. 3 over 2 times 10, we get 30 over 2, or 15. Minus 4 is 11. -5 times 1 is -5, plus 5 is 0. And we do the same thing with our other points. 3 over 2 times 1 is 3 over 2. 3 over 2 minus 4, so 3 over 2 minus 8 over 2 is -5 over 2. -5 times 0 is 0, plus 5 is 5. One more. 1 over 10 times 3 over 2 is 3 over 20. So we have 3 over 20 minus 4 minus 80 over 20 is going to be -77 over 20. -1 times -5 is 5, plus 5 we get 10. And so we have these 3 points here. If we plot them on our graph, we see that reflection, our shape, we're still moving the same direction away from our asymptote, but we're approaching the asymptote towards positive infinity now from the right instead of negative infinity as we were in our original function. You can see that shift to the left by 4. Our asymptote moves to the left by 4. And we can see that stretch, that vertical stretch that's happening combined with the horizontal stretch. It's kind of hard to tell sometimes exactly what the effect is, but in general we can see that it's stretched a little more vertically than horizontally, so that makes sense as well. So that looks reasonable for what we were expecting. Now we're going to go and look at the key features of this graph. So our original domain of log base 10 of x is always that x to the element of r as x is not less than greater than 0. We need a positive in our argument. Here, the stretch doesn't affect things because if we're positive and we stretch that, we're still going to be positive. So the only thing that's affected is in this new function is now our domain's shifted to the left by 4, as we found when we simplified that. So now we're going to be x is greater than negative 4. We're always to the right of negative 4. Our range, our original range is all real numbers. Y can be any real number. So that isn't affected by transformations. It's still going to be any real number. Our asymptote, equation of the asymptote, it was x equals 0, shifted left by 4. It's now x equals negative 4. Our y-intercept, we plug in 0 into our equation. So our x becomes 0. 2/3 times 0 is 0 plus 8/3. So negative 5 log base 10 of, log base 10 of 8/3 plus 5. We can calculate things with log base 10, so we just need to enter into our calculator negative 5 log 8/3 plus 5. We can punch that all in at once. So negative 5 log, we need brackets to make sure we're taking the logarithm of that whole 8/3 plus 5 equals approximately 2.87. So our y-intercept is 2.87 approximately. X-intercept, again, x-intercepts happen when y equals 0. So we sub in y equals 0 into our equation. We start off by moving that 5 over, so we get negative 5 on the left. Divide both sides by negative 5. So negative 5 divided by negative 5 just gives us 1. And now we can rewrite it into exponential form. So 10 base of our logarithm becomes the base of the exponent. This is our exponent all by itself. So 10 to the power of 1 equals 2/3 x plus 8 over 3. 10 to the power of 1 is just 10. So 10 minus 8 over 3 equals 2 over 3x. So 30 over 3 minus 8 over 3 equals 2/3 x. That gives us 22 over 3 equals 2/3 x. Divide both sides by 2 over 3, so multiply by 3 over 2. That's going to end up giving us x. 3's cancel out. We get 22 over 2, or 11 equals x. So our x-intercept is at 11, 0. So x equals 11, y equals 0. So that's the end of this unit, or not the unit, sorry, the end of this lesson. I'll post 2 more lessons on rate of change that we didn't quite cover before the break in order to get our test in. Of course, I was not predicting this current situation we were in, but I'm glad that we did get that test in. If you have any questions regarding your marks, let me know, because they will be based on the stuff we did before the breaks, those first 2 tests and the assignment. Again, next week I'm going to post an assignment on logarithms, so keep working through these lessons. Make sure you're okay with the homework, and then you'll hopefully feel relatively comfortable working through that assignment for next week. Again, as always, let me know if you have any questions at all through any means of communication you wish. Sometimes I can be a little slow answering just because I do get so many emails, but I will answer each and every one of you. But don't know when you're going to listen to this. Have a good day. Hope all is well, and you'll hear from me in the next lessons. Bye.